This video is for the classwork for section 24.4 and 24.5, where we are going to do summaries and then questions 13 through 18 and 31. So the second law of thermodynamics, the most important thing to know about this is that heat flows from hot to cold. It doesn't go from cold to hot. That's the same thing as if I had a Folsom Dam. Right, and here's water in my dam, which we have very low right now, obviously. Hey, gonna fill up recently because of the nice rain. But if I had Folsom Dam, and this is the dam, you would not expect that water to go from low to high. Same exact thing. We expect it to go from high to low. It's the same exact idea. So since water flows downhill, heat also flows downhill energetically. So the thing about this is we can get some work out of this. And when we do this, the work that we get is usually electricity. Right? Zappo. So that's what we got here, the work we're getting out of the dam. In the old days, you could use this dam to work a factory, that like a water mill, but now we use it mainly for electricity. So that leads us right to heat engines. Heat engines, instead of using the idea of water, what they're going to do is they're going to use a high heat or a high temperature, and then below they're going to have a low heat or a low temperature. This is usually ambient temperature. What I mean by that is like whatever it is today, and this is usually some sort of fire, right? So this is today's temperature. This is some sort of fire that we've made, and then we can get work out of this. And so if you look over here, the cars are a heat engine. We have gasoline and we have exhaust, and that's the work. But also one of the biggest things we do now is our steam engines have not gone away. Steam engines like locomotives, we tend to think of, oh, they're gone. They're not gone. They're just usually making electricity instead. So this is my QH. I've got gas. I've got nuclear even. I've got coal. I've got methane. Anything I can burn to make heat is going to heat up water. That's going to make those molecules really increase in energy, and then go through, and they're going to do some work here. And what kind of work do you think these are going to give us? It's going to give us electricity. Zappo. So, and this is my cool. This is my QH, my hot. This is my QL. So this is just regular life temperature, and this is my hot temperature. Along the way, we're always going to make some pollution, and this is thermal pollution. Thermal pollution means that we're pretty much releasing heat all the time. In our equation, we have work that we can get is equal to the difference between the Q high and the Q low. So I'm never going to have 100%, because I'm always going to lose some of this thermal pollution. There's nothing perfect. If there was, then all the heat would go directly into work, and that just doesn't happen. We don't see that. You would have to have zero energy or absolute zero given off, which is just crazy. It doesn't happen in our experience. So efficiency here, ideal efficiency is like a test. The way you can look at it is like an exam. So the hot is your potential. I have a potential of scoring 100 on a test, but I missed 25 questions. And so the way I get my efficiency is I say 100 minus 25 over 100, and it gives me an efficiency of 75%. Same thing with heat engines. We say this is our potential, our hot is our potential, and our cold is what we lose. Now usually this cold, like I said, is like room temperature or ambient temperature. It's not absolute zero. So in all intents and purposes, it's impossible to get this to 100% efficiency, because I can't lose no heat. I can't work at absolute zero. So quickly going through the questions, 13, hot to cold. This is work is done. I have a hot side and minus a low side. Thermal pollution we just talked about. I won't talk about it again. No, all friction wouldn't happen, because it wouldn't be 100% efficient, because we'd have to lose no heat energy. It's not going to happen. This one, we use that equation. The equation's found over there. The last one, last two, heat engines, the higher you run it, the more efficient. Go put it back into the equation and take a look. Here, pump a tire, work in plus friction.